Welcome to the Wine Lab. I'm Andreea Botezatu, and today we're talking about a wine problem that many people have smelled without knowing its name. Have you ever opened a bottle, leaned in for that first hopeful smell, and found rotten egg, burnt rubber, garlic, onion, cabbage, canned corn, or something faintly sewer-like instead of fruit? It is one of the more deflating moments in wine. You expect freshness, aroma, pleasure, maybe even a little ceremony. Instead, the wine smells strange, harsh, or vaguely alarming. And the first thought for many people is very simple. Is this wine bad? That question is exactly why today's topic matters to consumers as much as it matters to winemakers. Many wine drinkers have heard the terms reduced or reduction used to describe a wine, usually as a shorthand for a smell that seems off. You see, when people say a wine is reduced, they are usually talking about a wine that smells sulfurous, closed, or unpleasant because of a family of compounds known as volatile sulfur compounds. In practical wine language, reduction usually refers to sulfur-related off-aromas that tend to appear under relatively oxygen-limited conditions, or from the later evolution of sulfur compounds already present in the wine. It is not one single smell or one single molecule. It is a cluster of possible problems with different causes, different aromas, and different levels of persistence. That is also why reduction is not simply the neat opposite of oxidation in the way people sometimes imagine. In strict chemistry, oxidation and reduction are part of a redox system involving electron transfer. In actual wine conversation, though, when someone says a wine is reduced, they usually mean it is showing sulfur-related aromas that smell wrong, suppressed, or unpleasant. That could mean hydrogen sulfide, which smells like rotten egg. It could mean compounds that smell more like garlic, onion, cabbage, skunk, struck flint, or burnt rubber. It could even involve compounds that suggest cooked corn, asparagus, cooked tomato, or molasses. So, when people talk about reduction, they are usually describing a sensory problem. But behind that sensory problem sits a much more complicated chemistry story. And there is a useful terminology note here. In older wine and cellar language, people often use the word mercaptan for sulfur compounds associated with fault aromas like garlic, onion, cabbage, and rubber. Thiol is the more modern chemical term for the same family of compounds. So, in practice, when people talk about mercaptans in wine, they are generally talking about sulfur-containing compounds that chemists would describe as thiols. And that creates an interesting contrast because some thiols are highly undesirable and linked to reductive faults, while others are among the most prized aroma compounds in wine. In varieties such as Sauvignon Blanc, certain thiols contribute aromas like grapefruit, passion fruit, guava, and gooseberry. So sulfur in wine is not automatically the villain. I know, confusing, right? The difference is which sulfur compound is present, at what concentration, and in what sensory context. One can help create brightness and aromatic lift. Another can make the wine smell like my grandmother's Romanian kitchen. Sulfur faults are especially challenging because they can evolve over time. A wine may begin with a note of rotten egg, then move towards aromas that are more rubbery or cabbage-like. Some of those later compounds are harder to remove, and some may behave differently in bottle than they did in the tank. So what first seems like a small aromatic problem can turn into a much larger quality issue. Let's start with the most famous sulfur compound in wine faults, hydrogen sulfide, or H2S. Hydrogen sulfide is the compound most strongly associated with the smell of rotten eggs, and for many people that is the easiest sulfur fault to recognize. During fermentation, yeast can produce H2S as part of their normal sulfur metabolism, especially when they are under stress. One of the common triggers is a fermentation environment that is not giving yeast what they need to stay healthy and metabolically steady. Yeast strain, fermentation temperature, juice composition, nutrient balance, and overall fermentation health can all influence how much of it is produced. And this is where timing becomes crucial. If hydrogen sulfide is produced early enough during a vigorous fermentation, some of it may be carried off by the carbon dioxide being generated. That does not mean that the problem is harmless, but it does mean the wine has a better chance of shedding some of that volatile sulfur while fermentation is still active. If the H2S appears later, when fermentation has slowed, it is far more likely to remain in the wine. That helps explain why two fermentations that looked fairly similar on paper can end up smelling very different in the glass. And for winemakers, hydrogen sulfide is often only the first warning sign. If it is not removed or resolved in time, it can participate in the formation of other sulfur compounds, traditionally called mercaptans, such as methane thiol and ethane thiol. As I mentioned, these compounds are associated with aromas like garlic, onion, and rubber. In other words, the rotten egg stage can evolve into something broader, dirtier, and often more stubborn. That is one reason experienced winemakers tend to react quickly when sulfur notes appear. The concern is not only what the wine smells like now, it is what the aroma may become next. There is also a reason these aromas feel so immediately alarming to people, even outside wine. Sulfur-based compounds in the mercaptan family are famously used as warning odorants in fuel gases because the human nose detects them so easily. Natural gas itself has no smell, so odorants are added to make leaks noticeable. That does not make the situation in wine identical, of course, but it does help explain why mercaptan-like aromas in a glass feel so viscerally unpleasant and so difficult to ignore. They belong to a family of smells humans are wired to notice fast and to try and stay away from. There is also a sensory trap here. Hydrogen sulfide can be fairly recognizable. Rotten egg is vivid. But once sulfur faults move into faulty thiols, the aromas become harder to describe cleanly. One taster says onion, another says burnt rubber, another says garlic, canned vegetables, or skunk. Another simply says the wine smells dirty. These are not elegant descriptors, but sulfur faults are not elegant faults. They can flatten fruit, distort freshness, and leave a wine smelling as though something in it has gone sideways. Then we arrive at another important group, disulfides. Mercaptans can react with oxygen and turn into compounds such as dimethyl disulfide and diethyl disulfide, which are often linked with smells like cooked cabbage, onion, garlic, and more burnt rubber. These compounds are especially troublesome because they are less responsive to treatment than hydrogen sulfide or simple mercaptans. They also help explain why sulfur problems can seem to disappear and then return. When strongly aromatic mercaptans are oxidized to disulfides, the wine may smell cleaner simply because disulfides generally have much higher detection thresholds. In other words, the sulfur has not necessarily gone away. It has shifted into a form that is less easily perceived. Under more reducing conditions, some of these disulfides can be converted back into more odor-active reduced sulfur compounds, and the defect can reappear. It is very tempting when a wine smells sulfurous to think in broad physical terms. Give it air, stir it, splash it, fix it. Sometimes that instinct helps. Sometimes it makes the chemistry worse. Certain sulfur compounds can be transformed into forms that are harder to remove if the wrong intervention is used at the wrong time. So, sulfur fault management is not simply about acting quickly. It is about understanding what is actually present in the wine before deciding what to do. Okay, but what causes these faults in the first place? In broad terms, yeast stress, redox conditions, and timing. Yeast need a healthy fermentation environment, appropriate nutrition, suitable temperature conditions, and a fermentation managed with some understanding of juice composition, oxygen behavior, and nutrient demand. When those conditions are not met, sulfur metabolism can go off course, and some of the resulting volatile sulfur compounds can remain in the wine. That is why sulfur faults are often best understood as process faults rather than random accidents. They may begin with nutrition. They may be influenced by strain choice. They may be encouraged by fermentation stress. They may be shaped by lees contact, vessel conditions, oxygen exposure, or metal interactions later on. By the time the smell reaches the glass, the real cause may already be several steps behind you. When these problems appear, the solution depends very much on what compound is involved and when it is caught. Some issues can be prevented through good fermentation management, healthy yeast nutrition, and careful cellar decisions, while others require bench trials and more specialized intervention. The important point is that sulfur faults are much easier to prevent than to correct, and once the chemistry moves from simple hydrogen sulfide into more stubborn sulfur compounds, the options become narrower and the outcome less predictable. You may also have heard the old trick about dropping a copper penny into a glass of reduced wine. That idea is not entirely fictional. Copper can react with some sulfur compounds, which is why copper has a place in real winemaking practices as well. So, if you ever open a wine that smells distinctly of rotten egg, and you happen to have a real copper penny or a clean piece of copper around, you can try a small experiment. Pour a little wine into a separate glass, drop the copper in, give it a good swirl, let it sit for a minute, and then smell it again. If the rotten egg note softens, that tells you something useful about the kind of sulfur compound you may be dealing with. It is a fun little test and a surprisingly instructive one, but is still only a rough demonstration, not a reliable cure. It may help with some simple sulfur problems, especially those closer to hydrogen sulfide or simple mercaptans, but it will not fix every kind of reduction, and it is far less useful once the chemistry has moved into more stubborn forms, such as disulfides. So, how should we think about sulfur and reductive faults overall? First, they are often dynamic. A wine may begin with hydrogen sulfide, move into mercaptans, and later show disulfide-related aromas. Second, they are often deceptive. A sulfur problem may seem minor at first. It may appear to fade. It may come back later. It may suppress fruits so thoroughly that people describe the wine as dull, hard, or closed, without immediately identifying sulfur as the cause. Third, they are deeply tied to prevention. Good fermentation management, thoughtful yeast selection, and careful handling usually do far more for sulfur control than late rescue attempts. And finally, sulfur faults are one of the clearest reminders that wine is not static. It is a living chemical system, always shifting, always reacting, always carrying forward the consequences of what happened earlier. The smell arrives in the moment, but the chemistry behind sulfur faults often starts much earlier. The rotten egg aroma you notice tonight may reflect a stressed fermentation weeks ago. The burnt rubber note in a bottled red may come from sulfur chemistry that was never fully resolved. By the time the consumer encounters the problem, the wine is revealing the result of processes that began much earlier. So, the next time someone says a wine is reduced, it is worth asking what that actually means. Is it rotten egg? Or garlic, burnt rubber, cooked corn? A wine can smell sulfurous in more than one way, and those differences matter, because the more precisely we describe the smell, the closer we get to understanding the story behind it. And that is where wine science becomes especially useful. The aroma may seem mysterious. The mechanism usually is not. If you enjoyed this episode, buy a bottle, taste with attention, share it with someone curious, and appreciate how much chemistry can hide behind one glass of wine. And send me your questions, comments, or topic suggestions. My email address can be found on the podcast website page, and I always enjoy hearing what you'd like to explore next. Until next time, this is the Wine Lab. Stay curious. Cheers.